Welcome to Introduction to Deep Learning. We'll be tackling high-level definitions of fundamental concepts and the development leading up to the machine learning and key factors behind deep learning's rising popularity and future potential. Okay, so we can first talk about AI. AI, artificial intelligence, is the goal is to simulate human-like tasks or decision making, right? And we want to automate that, right? It can be programmed to perform human level ability, stimulating human logic, knowledge, rule bases, and such as the following, right? Using the inference engine, knowledge base, and algorithm, right? And we have a lot of different use case for that, right? For video games, medical expert system, delivery routes, okay? On the right hand side, you would see that deep learning is a subset of machine learning, and machine learning is a subset of artificial intelligence. Machine learning is still an automation of human tasks and decision making, right? And we want to identify the rules specified by a set of features or parameters to perform data processing, right? And again, you now program to perform the human level ability stimulating human learning via data and training, right? Your data is basically your input, and you do some processing, which is the training, and then you'll get the output, right? Training requires a way to measure the correctness, right, of the algorithm that you're going to use. And an example of that is using loss functions, which basically gives a feedback, right, to say the signal for use for learning, okay? Um, then you have the data, and you can have a lot of different data, as you can see, but it has to be normalized as well. You have to have correct data to teach, because it's garbage in, garbage out. Okay, so machine learning, you would see if you have rules and data, and you would have it as classical programming, then you'll get answers, right? That's our what we've been learning so far with our Python. But now we move away with, let's say, machine learning, right? With Python, we basically put training data and the correct answers, right? And then when we do machine learning, we'll get the rules, right? Now the rules, we can now put the testing data as well as the input, and then we'll get the answers. So here's an example with the face flipper where you have the training data and then you'll have answers as your input, right? And now you'll have a bunch of image with ups and down. This is your training data, and these are your answers, right? And you had engineered them, right? Meaning you just feed them the correct data, right? And then now, once you get your data plotted, right, you would see, let's say, the 2 green dots are the down, and the 3 red dots are the up, right? So you have this data that you want to put a boundary so that you can categorize each one with the downs and the ups, right? So that now defines your rule. You got this line. Now, with that line, if we now add another testing data, right, you have now the rules, which is this line, and you have the testing data, then you'll get a new answer, right? It will now predict a new answer. Now, this is an image without the answer, and the dot is now on the left side of that blue dotted line, right? Which means that it is part of that category, which is that is a downward image, right? See, there was the answer. Yep. So we go back again to machine learning, and this time around we want to ask what's the difference between AI and machine learning / deep learning, right? As we mentioned before, AI has a big scope, right? It has like machine learning and all other stuff, right? And with machine learning, it's more using the rules and training data, right? And you have this input and output, and in the middle is processing, okay? And you can see there's rules versus learning, okay? Again, now with machine learning, once we get the rules right, it will know how to predict better, so it learns, right? How about difference between machine learning and deep learning, right? Again, with deep learning now, you would have many different layers to reach an output. So you have input, and you have many different layers to process that, then the output, and you call them neural networks. Okay, okay. So as you can see on the left hand side, the bullet points, you have learning the important underlying features. So it tries to learn on its own without getting to know what are the correct answers, right? So it figures out by checking the pixel, lines, corner, letters, and that itself gives you an impression that it's graphical, so it's gonna use a lot of your graphical processing unit power, right? And then it uses the neural network, as I mentioned, produce a hierarchical representation of different features. Okay, the pixel, lines, corners, a digit, and also one of the purpose is to minimize the loss function, right? And using the feedback loop, right, while updating the weights. So it will keep trying to train its own model, right, the neural networks, through getting the loss score from the loss function, right? And the loss score, it will now be used by the optimizer so that the optimizer can update the existing weights, right? And so that we keep training the data until we get a good fit. Okay, so here's that graph that I mentioned, right? So let's say you have an input. There's layer one, layer two, right? After the last layer, it predicts, right? And then you would have the loss function. You'll get the loss score, and then the optimizer would now use that loss score to update the weights, and it'll keep doing that, right, until it gets closer to its target, right? So on the left hand side, so we have the weight. What is weight? It's bias factor towards better performance, right? um, Again, you may have like it's the same thing as what is more valuable to you, right, for what you have currently on your hand, right? So that's it. You would have many data points, and they would put the importance of each of the data points or data type, right? Next is the loss function, measures the correctness of the weight, right? This is the measuring, right? And optimizer is the updating, right? So that shows it. The training loop is the iteration, right? Then let's see. So difference between machine learning and deep learning, it's the use of neural network. Okay, so now it simulates like the human mind where it really learns on its own, right, without providing the correct data, right? So neural network in Python, now we have like a lot of cool modules such as TensorFlow, Keras, and NumPy, right? These are one of the things that we would need. TensorFlow is basically an open source platform for machine learning with a huge ecosystem of tools and libraries. So now next we have Keras, is an open source as well. It's a neural network library written in Python. It runs on the API of TensorFlow. It means that you would have Keras, and at the underneath the hood, it uses TensorFlow. Okay, and it provides very fast, deep neural networks with more intuitive and user-friendly modules. So again, it abstracts maybe the difficulty to set up the TensorFlow, right? And so that you can just go up and running and do your deep learning. And more abstraction, meaning less complexity to the user. So next is NumPy. It's a fast and efficient processing, n dimensional. So it could be 1, 2-dimensional, and x number of dimensional vectorizations and indexing, and provides a lot of mathematical functions, right? So an overview of TensorFlow. So TensorFlow in the middle, you can see that one, at the top left, you would see Google, right, supports the community, right? And who are these community? These are developers, whether they are in companies, right? They are researchers, open source, right? And then they contribute to keep building and maintain this TensorFlow, right? For TensorFlow, it requires Python, C++, and also NVIDIA, because NVIDIA really focuses on utilizing the GPU as deep learning processing, right? They're one of the known provider of GPU for deep learning. Okay, now it makes sense that why before GPU cards are video cards are very not super expensive, but because it's only for gaming. But now it's like it's being used for a lot of processing, and now the prices shoots up. Next is we have the tensor board, which visualizes your TensorFlow output, right? TensorFlow needs a platform, right? Again, it uses GPU multiple cores or GPU thousand of codes, right? So TensorFlow also uses Jenkins as part of its continuous integration and delivery, and it can sync it with your GitHub online repository, right? And TensorFlow also provides its repository online in GitHub as it is open source. So TensorFlow is an ML/DL framework developed by Google Brain Team and written in Python for numerical computation, data flow, and training and inference needed for deep learning, right? It's tensor plus flow. Tensor meaning it has multi-dimensional data representation, could be scalar, line, plane, volume, and flow is the pipeline, right? And various tensor operations on an n-dimensional, right? It uses both CPU and GPU, right? Next is TensorFlow can support CNN or RN learning architecture through different APIs, right? So it's pretty flexible. Use case include image recognition, voice recognition, time series, object detection in video, text processing, and a lot more, right? It helps you with classification, perception, understanding, and yes, prediction. That is the purpose because it's still part of AI, right? Next is the image classification, for example, is to label, right, this given object predefined classes using a set of features, right? So we have the features of, let's say, these three different flowers where they have, we identify the petal and sepal, right? And you would know which flower they are. So this is the very first, usually intro data set that you'll encounter for the TensorFlow, right? Next is you would see that now we've learned about creating this line, right, to do this classification, that boundary. So how is it possible now, right? So TensorFlow supports those feature columns. This functionality integrates raw data and feature, aka the estimator. So you first have the features, your input function, right? And you define what are the features. As you can see in flowers, you want identify the length, the width, and the length and the width of both sepal and petal. And again, that's why it's looking at the image, right? Define the batch size, and now for the feature column as well, you want to match it from the features, right? The input, right? And then now you have the estimators, right? To have that classification ready. Okay. Keras now is a high-level neural network API for Python. We mentioned again, underneath the hood, it's using TensorFlow, right? Very fast, very intuitive. We mentioned that already. Abstraction, user-friendly, and so on and so forth. Okay. The last thing is R can also use Keras. Okay. The core data structures of Keras are layers and models. Layers create a model, and the models can be defined and adjusted as you go, right? It provides essential functionalities required for DL, activation, loss, fit, evaluate, predict, and approach, etc., right? And you can see the code base now, like you import the library first and the models, the layers, and you want to create first a sequential model with dense layer using the add method, and now you would do add the different dense units, activations, input dimension, right? The other one like add units, again activation, softmax, right? So these are your models, right? Then you want to compile them. In the compile, you have three things that you'll need to think about: your loss function, right? Your optimizer. So again, your loss function is basically how it would measure. Your optimizer is how it would update, right? You may have a question of which optimizer to use, right? Basically, we can just use the maybe the SGD plus Nesterov for shallower networks, and maybe for deeper networks use Atom or RMS prop, and we'll see that later on, right? The fit method does the training in batches, right? And you would have X, Y training, and you have the NumPy arrays, right? If you remember your scikit-learn libraries, right? Next is you want to evaluate the model, right? And then you want to do some prediction, okay, to generate the outputs. So at the high level, as we mentioned, we get an input of an image without answers, right? Because this is deep learning. And then we have a hidden layer. This is what it's doing, training itself over and over again. And then the output layer, which would now, let's say, given a series of number, it's the highest probability would be a number 4, which is correct, right? Now if we now have multiple layers, right, in the neural network, it will have like this, more hidden layers, right? So this is now looking more like a neural network. And the more layers, the correct layers that are placed, the better your prediction is, right? And now, what are these layers? Input layer, hidden layer, and output layer, right? And as you can see, you would have the input that would include the weights, right, as your bias. And you have a summation function here, right? And then it becomes the activation function, which now provides you the output, okay? So here, weights are randomly initialized, right? Because it doesn't know yet, right? And then the feature representing the bias towards the digit 4, right? They are updated while minimizing the loss scores, right? So every time there's a loss scores, right, you want to update the weights again, and hopefully your loss scores is minimized, right? And keep doing that. Ultimate attribute that gets trained to discover the optimal set of unique weights representing the input. A biased neuron used in every layer, and it can translate the activation function to tune the layer, okay? So summon activation function, as you can see, the function would be multiply x and w, and they would sum them up as the summation indicates, right? So, and then you would just use this formula, and now you would see a data set could be like this or like this, right? In a linear approach, we can just have a boundary, like a one line, diagonal or straight, horizontal, vertical. That now question is, what if we have data set like this, and then now introduce the non-linearity to the network, right? So you can basically have something like this. So you can capture and categorize your different data sets, right? It allows to have arbitrarily complex functions to delineate different classes beyond the limited linearity, right? There's what you call ReLU, sigmoid, and tan. So for here, the single output node, right? All of these, if you remember your map reduced, it's basically trying to reduce that to a single output node, okay? It grabs all the input to create one output, okay? And this is through the help of the summation and the activation function, loss function, and fitting, okay? And when you have multiple output nodes, it will look like this. And now, instead of a single output, last time we were just checking if it's a number 4. How about now if we're checking about dog or a cat, right? So activation function, each neuron has this linear operation given that function. Essentially, weighted sum of its input x and add a predefined bias, and someone has to decide to activate or no activate, meaning take it or leave it, right? So if we're thinking about the neurological way, it's nerve firing and nerve not firing, okay? So the network is learning based on the activation function. you can think of, should the neuron learn to fire or not to fire, right? So at the basic level, we can simply use a threshold base if the weight plus the xt input, right, and the weight, is it greater than 0, or a threshold. For instance, you have the y hat, right? One meaning fire. If not, don't fire. As easy as that, right? This would be a problem when there are multiple classes to be classified, since all the neurons will behave the same. Since this threshold base only provides linearity, it will not learn when to fire. So again, neural networks that work in corresponds weight, bias, and activation function together. Purpose is to introduce nonlinearity to the output, right, of a neuron, so that it provides nonlinear transformation to learn and perform a complex classification or regression problem, right? It's going over and over again, so I don't need to mention these other bullets. Okay, a general guideline for activation functions. Again, we have the sigmoid. It's good for binary classification problems, so it's one or the other, right? The tan is similar to the sigmoid with stronger gradient, so it can show you different levels of colors, right? ReLU, backpropagation possible and be able to update weights and biases in a non-linear fashion, less computational compared to sigmoid / tan. Okay. General guideline, use sigmoid for binary and otherwise use ReLU. And you can see on the right side how your data point would plot, right, your function. Okay, this is your activation function, your sigmoid, your tan, and your ReLU. Activation function while modifying weights and biases, right? So you would have the input layer, hidden layer, output layer. We already know that, right? And as we go and train, right, at first it looks like a linear, right? And our goal is to make it non-linear because we're trying to solve more complex data points. And as you can see, the line now moves, right, to be more moves to the in a way that it provides the correct boundary to different classifications, right? As you can see now at the last image down here, the blue and green data points are now better divided, right? So the loss, which is the cost error function, right? It measures and monitors how accurate the network. Remember, it measures, right, for the weights and biases during the training. Your interest is to minimize the loss function to recalibrate the weights and biases, right? And neural network is trained based on the gradient descent. Gradient descent is an optimization algorithm used to minimize some function by iteratively moving into the direction of the steepest descent as defined by the negative of the gradient, right? So as you can see, this is slowly trying to move towards to create a more steep descent, right? And hopefully to make it curve, right? And then we saw this images already, right? This basically tells us how good our network is making at predictions for a given set of weights. The optimizer, so we already got the what you call that? So going back to measure, right? Now we update the weight, right? So in TensorFlow, right, we have ADA, which is adaptive moment estimation. It's one of the popular algorithms to use, right? And again, if you check around online, like you can use when to use what, right? You should Google what your use case. But generally, if you are doing shallow networks, you might end up with Nesterov, right? Deeper networks, Atom, and RMS prop, right? So, optimizer, right? We mentioned about the iterative optimization to find the global minimum loss scores with respect to parameters, okay? Learning rate makes it iterative, process faster by starting with bigger step, lots of learning, and smaller as the loss score gets smaller. Adjustment of stride depending on the score returned by the loss function. As you can see in this code, it will try to use the ADAM optimizer, right? And you would iterate over a batch of data set and keep doing that until you get all the points, right? And you want to get the gradients of the loss uh, weights, right? Next, you want to update the weights of the model, and now once done, now you can do some uh, optimization, right? And you can better predict your data. Epoch is a term used in machine learning and indicates the number of times while exhausting the entire training data set to update the weights that the machine learning algorithm has completed. Data sets are usually grouped into batches, right? Especially when the amount of data is very large. Do remember for deep learning, we really need a large data set, okay? With the training data set size of 60,000 samples, you can expect to have 2,345 gradient updates from Epoch, and training batch size arranged as below. Okay, so that might take a lot of time, right? And you do want to find your optimal number of epoch, okay? And that is through iteration. So the question is the lowest loss the better the degree of fitting? So again, we try to minimize the loss function, right? So let's imagine you're feeding the entire training set just one epoch, one batch, right? One time. How would you expect the quality of fit with the weight values? And let's say you imagine that you are breaking the training set into 10, 20, 30, and an increased number of epoch. What do you think is the quality of the weight value becomes? More the better? Answer is no, because you want to avoid overfitting, right? As the number of epoch increases, the more iteration of weights update those going from underfitting, optimum, and overfitting, right? So in the left-hand side, you may have just a small data size, right? And now you have a prediction that would go very, very bad, right? On the right hand side, you have the overfitting where now it follows all the data points. It doesn't really give you a prediction, right? It will only choose. It's like you taught it. It's what you taught it. It's that the training data, right? It only knows to predict the exact same one, right? And you don't want that. You still want a small amount of error. So just going back to the middle, see your optimum, right? So your prediction should not be like super 100% all the time. Um, what could happen? It means that maybe um, your training data set may be small and the prediction that you're trying to do for the next input, it's maybe the same, right? And if that's the case, it's not really helping your deep learning, the neural network, right, to learn correctly. So you want to feed different data as well, okay? So you want to land on the optimum. If you remember your linear regression, it's the same. You don't want to underfit and overfit. Just want to be at the optimum level. So, a summary to end this lesson. One is you assign random weights because you still don't know which one are the good weights, right? And then you use the input and then hidden node linkages, find the activation rate of hidden nodes, and then now you activation of hidden nodes and linkage to output, right? So you have input, hidden layer, and output, right? You find the error rate of the output node, right? That's through the loss function, and then now from the loss function we measured it. Now you want to optimize and recalibrate, right? Using the weights and errors found at output node, cascade down the error to hidden nodes, recalibrate the weights between hidden node and the input nodes, repeat the process till the conversion criterion is met, and using the final linkage weight score activation rate of the output node. So as you can see, it's trying to recalibrate the hidden layers, hidden node, and also the whole neural network. Okay, so if you do have a question, I know this is a very big topic. We have 4 chapters. Please, please, please send me an email, ping me in chat, so we can discuss further if there's anything still muddy or you need more clarification. Okay, till then, see you next week.